Okay, so we're going to attack the second part of this course, and that is going to be dealing with graphs and applications. And before I go any further, I'm trying out the Lightboard as a means to deliver the lecture itself, not only do exercises. This looks a little weird. I will try to make this shift to the left because you will see that the content appears in the middle, which is a little annoying. I think it would be better over there. We'll see if I manage to do this. And anyway, I'm hoping you will give me some feedback. Is this, for this type of lecture, so like a theory / exposition lecture, is this mechanism better than the one I've been using? Do you prefer the other way? I think the resolution is not quite as good here. The microphone picks up on a lot of noise. It's just over there. But anyway, let me know. So, graphs and applications. And I want to stress that we will probably be seeing more matrix results. I mean, not probably. We will be seeing other stuff related to matrices because matrices and graphs have a very tight connection. Okay, and I will make this clear as we progress. To begin with, let me sort of explain some things that are going to be recurrent here. So the first thing I really want to stress is that you probably have heard about networks, and what we are going to be talking about is not really any different. The difference in terminology is mostly a matter of where you're practicing graphs or networks. In mathematics, we tend to use the term graph, usually, and a lot of other disciplines talk about networks. This is a math course, so we'll talk about graphs. Just be aware that they're essentially the same things. It's just another name for the same thing, typically. Now, the way I'm going to present things is based mostly on a book by Berger, who's a French graph theorist who did quite a lot of work setting up the domain. And that's a book, it's quite an old book, but it remains a very interesting book. And there's a more recent book, much more recent book by Bang, Jensen, and Gutin that I will be using for some material as well. These are like hard books. Don't expect to open them and find your way around. There's probably much better textbooks for some of the aspects of what we're doing, but I mean, you have to choose something. Much of what is in those books is relevant. Let's put it this way. Now, one thing that I will point out: graph theory, and in particular, if you start to veer off into network theory, this is a domain where the terminology is not really fixed. In the mathematical side of things, things have more or less gelled into something that is coherent. But even there, it is not always clear that we'll be sort of always talking about the same thing in the same way, I mean. And so I'm going to try as much as possible to give you a sense of when there's a vocabulary change, for example, point out differences. Just be aware, I mean, when you're opening a textbook or a book on graphs or on networks, you will meet a lot of different terminology. You just have to sort of often take a step back, go to the first chapter, which is where the authors typically define everything that they're going to be using. Okay. So, what's a graph? And I will use pen, plural, to illustrate things as we go. I'll also have examples written out. I mean, one of the advantages of using the board is that I can squiggle as we go. And I will, before I get started, open, oh gosh, open one of those new pen things in case I need them. Okay, so what's a graph? First, and I want to warn you, this lecture today is going to be quite substantial in terms of definitions and the like. We're not going to look at any proofs in this particular video, but we will be going over a lot of definitions. You don't have to know them, you just have to know where the definitions are in order to be able to refer to them when needed. So intuitively, a graph is a set of points and arrows joining these points, potentially. So I can think of them, typically I would have some points and some arrows joining these points, for instance. Okay. And the points we call vertices, and the arrows we call the arcs. And I'm going to make a distinction right away that we'll come back to soon, but what I drew here, this is an arc. It has a direction. Okay, it's an arrow with a direction. I could have drawn the same thing without directions. In that case, we would speak still of vertices, but of an edge instead of an arc. Okay. So that's going to be a distinction. The graph on the top we'll call directed, typically, and the graph on the bottom we'll call undirected. Okay. Now let's get going with the beginning of the definitions. So a graph, in practice, is a pair, x and u, where the x is a set of elements. These are the vertices. Okay. And u is a family of elements. So they are not points or vertices, because what they do is, if you see, they are elements of the Cartesian product x times x. Okay. So this means an element of u is something of the form u1 would be, for instance, the pair x1, x2. Okay, this is what this means. The elements of the Cartesian product means that those elements, one is in x and the other is in x. And what they represent are the arcs. So for instance, if I had called this x1 and this x2, this u1 here would be the arc from x1 to x2. Okay? So often we'll number these arcs. So I could, for instance, call this guy 1, this guy 2, and this guy 3. Okay, and this is what this statement here is saying. The family is often denoted by the set of its indices. And we can have an element xy more than once. Okay, so I can have something of the form x1, x2, and let's say 3 arrows going from x1 to x2. Okay. graph in which there's only one arrow from one point to another, one vertex to another, is what we, well, first of all, let's start with the general case. This would be what we would call a free graph, because there are three arrows between x1 and x2. And we look at all the set of arrows, all the set of vertices, and we look at how many arrows there are between all pairs of vertices. The largest such number is P. If it's P, then that's what we call a P graph. Okay. And a lot of times in this course, we're not going to worry about P graphs. We're going to worry about one graphs. Okay, there will be only one arrow in one direction between any pair of vertices. Now, the order of the graph is the number of vertices in the graph. Okay, this is quite simple. The two graphs on the top there have order 3. They have 3 vertices. The graph on the bottom here would have order 2. It's got 2 vertices. If I have an arc that goes from x to itself, this is called a loop. Okay. And when we look at an arc, we can look at the initial vertex. So if I'm looking at this arc here, the initial vertex is the initial endpoint, and the terminal vertex is the terminal endpoint. Okay. And we say that this vertex is a successor of this vertex if I have an arc that way. Or we would say that x1 is a predecessor of x2 because there is an arc from x1 to x2. Okay? All of these notions, if you think about them, they're very intuitive. Okay? They describe relationships between objects, and we'll talk about a predecessor or successor because something comes after something or before something. Okay. Typically, there is this thing that we see here, which consists in extending this. And so, for instance, if I'm looking at x2, I can look at the set of all its predecessors, which would be denoted gamma minus. Okay, it's this one here. Gamma minus will be all the predecessors of, I'm trying not to go over gamma minus, and that is going to be x1 and let me call this x3, x1 and x3. Okay? And then we call neighbors of a vertex anything that is either a predecessor or a successor. Okay. Now, these are two graphs. So what do we know how to say about these graphs for the moment? That graph on the top, it has 1, 2, 3, 4 vertices, so its order is 4. It is, you can see here there are 3 arrows, 2, 3, and 4, going from A to B. There's no more than 3, so it's a free graph of order 4. Okay. Whereas the graph on the bottom has vertices x1 to x6, so it's order 6, but you can see that there are no more than 1 arrow in each direction between any pair of vertices, so it's a 1 graph. So this is a 1 graph. Of order 6. Okay, so a concept that I've already talked about, but that we're going to look at in a slightly more general context here, is directed versus undirected graphs, and a bit more general than that even. So, as I have already said, if you think of an arc, it defines a continuous line joining two vertices. If I don't specify the direction of that arc, or if I think of the direction of not being important, then we have what we call an edge. Okay? And so the same way as we've done with arcs, we can refer to edges by their index rather than by their actual nature. Okay? When we have a graph where we're not caring about the direction, we call that an undirected graph. Another name that is not, I believe, not used too much these days is multigraph. We tend to use multigraph in another context these days, but okay. If there's no loop in an undirected graph, and that each edge, each pair of vertices is joined by no more than one edge, then we call that a graph that is simple. Okay, that is quite an important concept, and we'll see it over and over again. Recently, I mean not recently, but in more modern texts, typically what we call a digraph or directed graph is a graph that has arcs, so that has a direction, but also has no loops. So remember, we saw that a loop was a structure that ended up back at itself. If we have no such arrow, then we have a digraph. This is not completely homogeneous. Some people will call digraph anything that doesn't, well, that can have loops, but no parallel arrows. Others remove the loops. And again, as I said, when you're looking at a text, you have to sort of go back to the beginning when they're defining things to see which is the case that you're dealing with. Now, we say that two arcs or two edges are adjacent if they have an endpoint in common. Okay, so if I'm looking at this graph, these two vertices are adjacent because they have an endpoint in common. They could be like this. These three vertices are adjacent because I'm not imposing the direction of the connection. Okay? It just means one of the endpoints, either the initial or the terminal endpoint, is the same, and therefore I have adjacency. Okay? The multiplicity of a pair is the number of arcs with initial endpoints x and terminal endpoint y. So this, remember, is exactly what we saw before. This pair xy would have multiplicity 2, okay? Because if this is x and this is y, then the initial endpoint, yes, this is m plus g of that xy would be 2. And there's the same way we can define m minus as the other direction. Okay, so you see this m minus is just mg plus of yx. So here I'm considering this direction rather than that one. This, I should point out again, this is not something we are going to look at a lot. But it might come in useful from time to time. So it's worth having a definition somewhere. But like in general cases, we'll be looking at simple graphs or simple directed graphs. We won't be bothering about a variety of arrows, but it can happen. So you see all these definitions. One thing that is important and that happens a lot in graph theory and which is what you're seeing here at the bottom, is that oftentimes we'll be interested in properties of set of vertices, not only of one vertex, but of a bunch of vertices. So we'll define properties as relative to a set rather than just a single thing. So here you can see, for example, we're defining two subsets of a set of vertices, and we assume that those subsets are different. And we can define the multiplicity from one set to another as the multiplicity of the arcs that join the points in the two sets. Okay, we'll come back to that, not with multiplicity, because as I said, this is not something we'll spend a lot of time on, but it will be a very common way of looking at things, not only as one vertex, but as a subset of vertices. Arcs incident to a vertex is defined the following way. So if I have a vertex x, and it's the initial endpoint of an arc, and that arc is not a loop, okay, so I have a vertex x, say, so let me remove this one. I seem to have, by the way, become a bit better at erasing. One of the reasons I was hitting issues is that I'll show you, I'll make a little video, I think, where the previous video I made, I actually took out the sequences when I was erasing the board, because that took me a long time. I seem to have got a bit better, so it might be a feasible option to use this. Okay, so if I have a vertex that's the initial endpoint of an arc, so this is what I have here, x, then we say the arc is incident out of x. Okay, and this is a very, very important notion. So if I have x, y, x, z, and x, u, say, I shouldn't write u because we're using u for the arcs, t, let's say. Okay, the number of arcs incident out of x plus I would add something like this that would count also as in that count. When I count this, I get this thing here, dg of plus of x. So this is the outer dummy degree, okay? We'll often talk about the degree, but you'll see it below, okay? And the same way, we can talk about the inner, or inner dummy degree. And so, for example, if I take this vertex y here, its inner dummy degree is 1. Okay, the outer, so dg plus of x here is equal to 4, and dg minus of y is equal to 1. Okay. And the degree of a vertex is the number of arcs that have x as an endpoint in both directions. Okay, so if I'm looking at, let me add r, if I add an arc here, then the degree minus of x here would be 2, because this is also an incident arc, okay? It's both an incident out and incident in. Okay, it comes in, it comes out. So dg minus of x is 2, and the degree of x is then 6. Okay? And that's very, very important. I'll give you an analogy, case where it's where it happens all the time. So I work on infectious diseases. One way that we have of considering how the disease is propagating population is to look at contacts. And a contact can be described by a graph. Okay, so let's say I have a disease, I'm in contact with you, so I'm transmitting the disease. Okay, so this is an arc incident out of myself. And when you're considering, let's say, a smaller population and you want to know what the dynamics of the disease is, it's important to find out what the degree distribution is in that population, because that is going to tell you. So if everybody has a low degree, so not a lot of people make contacts, then the disease is going to have trouble propagating. But if, like, someone in your population, for example, ends up infected and they are making tons of contacts, we typically call them super spreaders, because what they do is, well, they make a lot of contacts, and therefore it's important as a source of transmission. Sorry, I took a little break. I'm taping at the end of a corridor in the math department. It's 20 past 8, and I was surprised because someone was apparently going around, whereas I was expecting it to be empty. So I hope we're not interrupted by security or something like this, because it's getting quite late, but it's more quiet. Okay, so degree, as I was saying, is very important in determining the capacity of a graph to do things. And I mean, this is important in, as I was saying, in disease transmission, but there's a lot of other contexts in which the degree distribution is important. Okay, so we will come back to degrees many times. And as I was pointing out earlier, oftentimes we look also at properties of set of vertices. So if I'm thinking about a subset A of the set of vertices, and I have, and you'll often see this when we're describing a graph, we'll draw, when I was in France as a student, we called that a potatoid, potato-like structure, and that is going to be a set of vertices, okay? But that is what we're denoting A here. So we've got some vertices here, and if we look at that definition, an arc incident out of that set, if we have an initial endpoint that belongs to the set and a terminal endpoint that does not belong to the set, then we say that the arc is incident out of that set. Okay, so there can be connections within that structure. But what is important is connections out of or into. Okay, so we call W plus of A the set of arcs incident out of the structure. So that's going to be a bunch of arrows going out. And then we have a set of arrows going into a structure, a subset, from other sets of vertices, or just one, it doesn't really matter. And this is what we call the arcs incident into. Okay, and so the set of arcs incident to this A here is the union of the incident out and incident in. Okay, let me erase. Now let's talk about symmetry in a graph. So a graph is symmetric. First, let's look at the general context. So if I have a graph that has potentially multiple arcs between vertices, so that we have this definition in terms of m plus and m minus, if the number of arcs in and out of a vertex is equal for all pairs of vertices, then we say the graph is symmetric. The simplest symmetric graph to look at is when you're looking at a one graph. Okay, so if I've only got one arrow in each direction, then we say the graph is symmetric if whenever I have an arrow in one direction, this is what this is saying here, if I have an arrow in one direction between x and y, then I have an arrow in the other direction. Okay. A graph is anti-symmetric, and again, we have the general definition in the case of multi-arrows, but let's look at the single arrow case. If we have a one graph, then the graph is anti-symmetric if and only if the presence of an arc in one direction implies absence of the arc in the other direction. So I would have something like this, but I would not be able to add something like this. This graph here, oops, make this a better arrow, this graph is not anti-symmetric. This one is, okay, because I have no reverse arrow in any case. Not having an arrow is okay, but if I have an arrow, I can't have another one in the other direction. The graph is complete. And again, let's jump right away to the one graph case. A graph is complete if and only if I can find an arrow whenever there isn't one. Okay? If there's no arrow here, then I have an arrow here. Okay? This is what we call a complete graph. We will see more on complete graphs later on. Okay? This doesn't say that I can't have this. Okay? It just says if I don't have one, then I have one in the other direction. Okay? A clique. So if I have a simple complete graph on vertices, this is an n-clique, and it's denoted Kn. You will see this is again something we'll come back on, because completeness is something, it's an important property of graphs. A graph that is complete is essentially a graph that has most of its arrows, typically all of its arrows on. And so in terms of diffusion of stuff, whether it's disease, but also whether it's information or whatever can be described by flow along a network or a graph, this complete graph, of course, ensures that you can make contact with every other vertex that is there. Okay. So, as I said, we'll come back to that. A bipartite graph is a graph where you can partition the vertices into two sets, and in such a way that none of the vertices in the two sets are, in each of the sets, are adjacent. So, typical example of a bipartite graph would be something like this. We often write them in two columns because that makes it much easier to think about. If you think about this, here, what this is saying is none of the vertices, if I call this x1 and this x2, none of the vertices in x1 are adjacent, so have an arc in common with other vertices in x1. And bipartite graphs are also very, very important, and we'll meet them again. We can add completeness as a requirement, and then we define what is called a complete bipartite graph. And if you have a simple graph, remember simple means it doesn't have orientation, and if we have a simple complete bipartite graph, then this is a graph that we will see again, which is KPQ. Okay, the you will see there's a standard, relatively standard notation for graphs and digraphs, because some of them have very important properties that are really fundamental, and so we need to have sort of accessible names for them. Subgraphs. So a subgraph is a new graph, essentially, that's generated by considering only the vertices belonging to a subset A of the original set of vertices. And a subgraph contains all the arcs that link vertices within the graph, the subgraph, and none of the others. So let me take an example. This is very important, okay? It comes up very often. And let me say this. Now, if I take as the set A the vertices in the box, the pink box that I'm highlighting there, then the subgraph generated by A, so if this is A, the subgraph generated by A is this subgraph. So I can only keep the arrows if they are between vertices in the subgraph. So that subgraph is, what do I have? Is this one. Okay. We have, we can also talk about a partial graph, and remember, so notice, not remember, that here I'm generating by taking a subset of the vertices, and as you have probably understood by now, I can think also in terms of the arcs. And so here I can talk about a partial graph, and that partial graph now is generated by considering not vertices but arcs. Okay? So if I take a subgraph in which I have the arcs that belong to a set V, then here I would get the same graph here if I said what I want to do is keep those two pairs of arcs. Okay? But I can think of them that way also. Okay? And as I stress, this will be common in graph, in what we see here. We often reason from the perspective of the arcs or from a perspective of the vertices. And sometimes the terminology is different, but when you think about it, you're talking about the same thing, except that you're talking about the arrows or you're talking about the points, the vertices. Okay, so now we start on something that is extremely important in graph theory, and that is going to be very important for us in the analysis of whatever data we end up looking at. It's chains, cycles, and this type of thing, paths, etc. So let's start with chain. So a chain is a sequence of arcs, such that each arc in the sequence has one endpoint in common with the predecessor in the sequence, and the other endpoint is in common with a successor in the sequence. Okay. So it's simply, look at this here, for instance. I have, if I take this sequence, this is 1, 2, 3. I'm labeling the arcs, just labeling them in a way that's convenient. This would be a chain, and it would have length 6. Okay, I would go along 1, 2, 3, 4, 5. Not 6, 5. I can't count. Okay, so this is a chain. If a chain does not go through the same vertex twice, which is not the case of the chain I was just demonstrating here, we say that the chain is elementary. And if the chain does not use the same arc twice, it is simple. So that chain that I was describing over there is not elementary because I've met that vertex twice. But it is simple, okay, because I have not used the same arc twice in this chain. Now a path is a chain in which the terminal endpoint of an arc is the initial endpoint of the next arc. It's essentially the same thing as a path, as a chain, with very little differences. We're going to use them probably a lot. And we'll use them in one graphs, as the example over there. So if I have a one graph, what's important is that I can think not only, this is the theme that I was talking about before, if I have a one graph, my path, I can think of it also in terms of the vertices the path traverses, because my path is defined as a function of the arcs. Okay, it's a chain that I'm following. Okay, but because I've got only one arrow in each direction, I can also say that chain, that path, is actually going through this, and this. Okay, so I can write as a sequence of vertices rather than as a sequence of arcs. Okay. Do I want to say anything else? Just for precision, I'm looking at a camera, a TV over there where I'm seeing myself. So that's why I'm looking like this, because I'm looking at what is projected on the screen, and I can see there. So that when you see me looking strangely, it's because I'm looking at a TV which is far away. Okay, no, I think that's about it. A cycle now is a chain in which two arcs do not appear twice. Okay, sorry, an arc does not appear twice. So an arc, we don't use the same arc twice. Okay, sorry. And additionally to that, the endpoints are the same. So this is a cycle. Okay, I've used each arc only once, and I've initiated and finished my walk through the graph at the same place. A pseudo-cycle is like a cycle, but I can take the same arc twice. So going 1, 2, 3, 4, 5 gives me a cycle. But I could also go 1, 2, 3, 4, 3, 4, 5. Okay, so I've gone boop, boop, over boop, boop, once more. What I have is a pseudo cycle, not a cycle. And a circuit is a cycle where you end up okay, the difference, don't worry too much about it. The difference between circuit and cycle is a little subtle. I will probably do more advanced examples when we come to that. A connected graph. So this is really, really important, and that's something we are going to, that's one of the first topics, a bit more detailed topics that we're going to look at. A connected graph is a graph that contains a chain from X to Y for each pair of distinct vertices. Okay. So this, for instance, is a connected graph, because wherever pair of vertex I take, I can go from that vertex to this vertex through a chain. Okay, and I can take any such chain and I will get there. This is not a connected graph, because if I'm here, I cannot get here. Okay? Or if I'm here, I cannot get here. Think of, and I mean, there will be analogies, those of you who do probability, there's something called a Markov chain, and it's really useful to think in terms of following paths. Okay? And this is going to be important in the future. So here, you cannot go from here to there, because there's no arc to follow to go from here to there. Okay? So this is a connected graph, this is not a connected graph. And actually what's very interesting is that graphs, connection defines what's called an equivalence relation. So an equivalence relation is what's called a binary relation, which connects elements. And it's a binary relation that has the three properties listed here: reflexivity, symmetry, and transitivity. And what's really nice with equivalence relations is that they allow us to think in terms of set of entries, or a set of vertices here, which is going to be, that share the same property, that are in relation with one another. Okay, so what this means here, okay, if I denote x we typically say equivalent, x equivalent to y, the relation that says x is either equal to y, so a vertex is the same, or they are different, and there's a chain connecting x and y. Then that is as those properties. You see, so if this should be, well, let's see if I can do that. I was told I can do that. This should be x here. So the element is in relation with itself. Well, obviously from this definition, either x equals y, and this is what we have here, reflexivity, x is equivalent to y means that y is equivalent to x, which in terms of this means that if they are in the same, they are connected, if this one is connected to this one, in terms of being able to find a path from here, it means that this one is also connected to here. Okay. And the last one is transitivity. That means if two pairs are in relation to one another, then the ones that we have not assumed are in relation to one another are in relation to one another. Okay, so if x is equivalent to y and y is equivalent to z, then x is equivalent to z. And we can go further. So a connected graph, that's going to happen often, but maybe not as frequently as a graph that we can decompose into its connected components. So I pointed out that this graph here is not connected, okay, because these two vertices have no access to this one, and this one has no access to this. But I can look at subsets of vertices in the graph in which connectedness happens. Okay, this one is connected to itself. these two are connected one to another. And so these two things, these two sets of vertices here, are what we will call the connected components of this larger graph that we have here. So this graph is not connected, but each of its connected components are connected. Okay. Time for more erasing. Now, if I have a connected graph, what we call an articulation set or a cut set is a subgraph, so the set of vertices A is a cut set or an articulation set. If by removing these vertices, I am depriving the graph of connectedness. Okay, this is really important. The examples that we're going to look at in terms of applications in this course are probably going to involve social networks of some sort. Okay? And if you think about social networks, the way they organize is, well, there's a variety of ways they organize, but if you think about how it works with your friends, you could have, let's say, a large group of friends, and you could realize that this group of friends is susceptible to explode if a certain person stops coming, because that person acts as a bridge between two sort of more connected subgroups. And that is something that is observed in social network theory, and we'll come back to that. Okay, so this is what this means. And I'll have, let's say, a connected graph consisting of two nicely connected subgraphs, okay? So suppose this one is almost complete. I mean, there's arrows everywhere. And then I have entries here. Well, if, for example, this person here, and I'm not making a connected graph, so it's a little silly, but if this person here is your only link to another nicely connected graph here, and this person is removed, and of course you need things in both ways, let's say like this, then these become two disjoint, they become two connected components. Okay, so this here is an articulation set. So a single vertex, but this is the idea. It's a set of vertices which, if you remove them, you lose the connectedness. We call stable set a set such that no arc joins distinct vertices in that set. Okay, we'll come back to that, I think. Now, one very important component. So some of you have asked me, is this the end of linear algebra? And no, it's not, because of that guy. Okay, if you have a graph, you can associate to it a bunch of matrices. So one of them would be the matrix that has entry Aij, the number, remember this is the multiplicity of xi, xj, so that would be the number of arcs between xi and xj. And if I look at the matrix that I get, so typically, if we have a one graph, then we would have one if we have an arc between xi and xj, okay? And a zero otherwise. So if I have, let's call this matrix, this vertex x1, x2, and then x3 here, then the matrix associated to this is, so I have Aij equal to the number of arcs from I to j. From 1 to 2, I have one arc. From 1 to 3, from 1 to 1. Hey, sorry, 1 to 1 first. From 1 to 2, I have one arc. From 1 to 3, I have 0. I'm not talking about chains or paths. I'm talking about arcs. From 2, I have an arc to 1. I have no arc to myself, and I have one arc going to 3. And from 3, I have no arcs. So this is a matrix that describes outgoing arcs, but I mean, as you can guess, we can look at it the other way and see incoming arcs, because I can take this column here and think about what's happening in terms of things, arcs arriving at x2. Okay? And this is what we call the adjacency matrix. And we'll come back to that. But so there's a distinct link between linear algebra and graph theory because of that. Okay, that matrix is really going to be useful, and you'll see that when we're talking about connectivity, this will be very, very useful.